All right, we are in the 5.2. 5.2 notes. We left off on these ones with double U substitution. So we're just going to do a couple of these examples with natural log now. Great problems. Okay. So still with indefinite integrals, we'll do a couple with bounds today, but you guys know how to do them with bounds. It's exactly the same. You just have to either change your bounds in terms of U or like re-sub back in what your U is before you plug in the numbers and use like the fundamental theorem of calculus, but we'll get there. So on this first one, if I see this setup, I'm probably tempted to let U be like that x plus 1 because it looks like it's inside, okay? And then you might be like questioning yourself because you're like, well, the derivative of x is just 1, so I still have that other like 2x located in the integral. So this would be a case where I'm probably going to have to use like that double U substitution. I think I want to turn the lights on. I think I like this vibe. Oh yeah, much cozier. Okay, so what we'd probably first try is letting U be x plus 1. And I would do my normal du dx is 1. So du is the same as dx. Okay. So right now I'm here. And I let u be x plus 1. So I have that squared. And then du is the same as dx. And then I could be substituting that in like so. Now you don't have to write this down, but I still have this like 2x kind of like left up here. And this is what I can't have. I can't have something in terms of x and in u. So what I could do with the 2 at least, is I could bring the 2 in front, the constant in front. That's probably what I would do with the 2. And then I still have this x. So what we're going to do is we're going to take our little equation that we let u be, and we're going to solve it for x. So I'll just kind of do that up here. Well, maybe I'll come down here. Solve this for x, and I get x is the same as u minus 1. So now I can double substitute x for u minus 1, and now I have everything in terms of u. And I do think there was a couple on that circuit where you had to do a double u substitution, maybe 1 or 2. All right, so now I'm looking at my work. Everything's in terms of u, so I'm like, okay, that's good. Before I anti-derive this, I would probably simplify this integrand a little bit. So I could rewrite this as like u over u squared minus 1 over u squared du, which that would give me 1 over u minus u to the negative second power. And again, when I see that 1 over u, I don't want to rewrite that as u to the negative first power. Now I'm recognizing the antiderivative of 1 over u would be my natural log. But the u, anything else besides just a power of 1 in your denominator, rewrite as a power, and then you can just undo power rule. Okay, we're ready to antiderive here. So the antiderivative of 1 over u is the natural log of the absolute value of u. And then this piece minus add 1 to the power, that'd be negative 1, divided by the new power, plus c. Okay. Then I'm going to back substitute in what I let u be, which was x plus 1. I'm going to keep this in parentheses. Okay, this right here, where do I want to go? I would change that. That's the same as plus
Just 1 over u.
Yeah, plus 1 over u. I'm just trying to think where to show my work there. Plus 1 over u. So plus 1 over what I let u be, which is x plus 1. So we have all that plus c. So if you want to distribute the 2 through, you could. Like you could leave your answer like this. That's how I left my answer. This would also be the same as or you might even see it written like this. Putting that power back on that one. So maybe just jot these down as, like, recognize these answers, but I'm A-okay with you stopping there after you plug those back in. And I forgot to put brackets around my 2 on my key, so don't forget about that. Okay, that's fun. Let's try another one. All right. So this one you might be tempted, you're like, okay, should I let u be just the square root of 2x? Should I let u just be 2x because that's like inside the radical? And in this case, we're going to let u be our whole denominator. Okay, we're going to let u be our whole denominator. And that is kind of one of my like tactics when I have more variables in the denominator, okay, because I'm thinking I might have to use natural log. So u is the same as this. Okay, this one's kind of tricky. So du dx, 1 is just 0. This would become 1/2, 2x to the negative 1/2, chain rule times 2, times the derivative of the inside. So those end up canceling. And I get, this would be the same as 1 over the square root of 2x. Okay. Here's the tricky part. Let me substitute in like what I have right now. So this is what I have. I have 1 over what I call u. And you're like, okay, but somehow I have to plug in this 1 over square root of 2x, and that's like nowhere in my integrand. So what we're actually going to do, we haven't done one like this, is we're going to put, we're going to use what we originally let u be, and we're going to put this piece in terms of u only, okay? So up here, I have that u is the same as 1, right over here, u is the same as 1 plus the square root of 2x. So what I'm going to do is I'm going to algebraically solve this for 2x and then plug that in here so I can get this in terms of u. Okay, kind of a weird one. So u minus 1 is the same as the square root of 2x. So that du, which is 1 over the square root of 2 dx, is the same as 1 over u minus 1 dx. Okay. So solve this for dx. So that's really what I'm substituting in here. Now I'm going to replace this dx with this u minus 1 times du. sounds kind of weird. Because you're like double U substituting in the U substituting like process, not even like in the integral, but like in our U substituting process. I would say these are probably about as hard as the natural log ones are going to get. Okay. So similar to before, I'm going to kind of clean up my integrand a little bit because that's the same as U minus 1 over U. So I could break that up as U over U minus 1 over U. So then I'm just getting 1 minus 1 over U du. Okay. Antiderivative of 1 would just be U minus antiderivative of 1 over U. It's the natural log of the absolute value of U plus C. And then we just resubstitute in what we let U be, which was 1 plus the square root of 2x. Okay. So U1 plus the square root of 2x minus the natural log of the absolute value of 1 plus the square root of 2x plus C. Make sure that's right. Oh, in our final answer, we technically don't need this 1 plus because that's like kind of a part of our constant. So the back of the textbook would probably have this as an answer, just the square root of 2x minus the natural log of the absolute value of 1 plus the square root of 2x plus C. Because since we're letting C be any constant, whether we have a plus 1 or not, it doesn't really matter. Okay. I did want to point that out. Okay, that one makes sense. That pattern's kind of hard to like recognize. Yes, sir.
Why did the antiderivative of 1 be? Oh, no, I see it. Okay. I was wondering why the 1 became a U, but I was just like.
Yeah, sometimes people will see that and they're like, oh, it's just 0. You know, they like think it drops out. They think derivatives. Going backwards with integrals. Okay, other questions? Okay, let's try a little easier. Solve this differential equation. So remember, a differential equation is an equation that contains a derivative. So this is like our slope equation of something. This is our slope equation. Think of this as like our first derivative. So when they ask us to solve this, they want us to find the antiderivative. They want us to find the general solution. That when I take the derivative, I would get this differential equation. That's what that means. Okay, so we do that with integrating. And I put one of these, I think, on the test, and I think all of you knew to integrate it. Okay. So I'm looking at this, I'm like, whoa, this one has natural logs in it. But I know the derivative of the natural log of x is 1 over x. So I kind of see that within my integrand. So that gives me a hint of what I'm going to let u be. I'm going to let u be the natural log of x. Okay, so again, like I was just saying, because I know the derivative of the natural log of x is 1 over x. So since I kind of see that 1 over x within my integrand, that's kind of my hint to let u be the natural log of x. So du is the same as 1 over x dx. And I see that right here. 1 over x dx. So I let the natural log of x be u. And then the 1 over x dx. I like that. 1 over x dx. I'm going to replace with du. So I just have a 1 up there. Okay. What's the antiderivative of 1 over u? Natural log of the absolute value of u plus c. And then we back substitute in u, which was natural log of x. So the natural log of the natural log of x. I'd probably put y equals in front since we did technically solve this. Or you could do like capital F of x if you want. And remember, folks, I probably should have pointed this out when we were doing some of the easier ones. You can always check your answer by finding the derivative. So like this one, for example. You can always check your answer by differentiating this to see if you get back to here. I can do it really quick. I'd probably bring this power down. Derivative. Carry the constant down is 1 over x. Yep, we get back to here. Now, obviously, these ones would be a lot more complicated to like check your answer. But this one, you could do that as well. So we have let's go ahead and find the derivative. We'll do this notation. So here I need to do chain rule. Derivative outside is 1 over natural log of x. Chain rule times the derivative inside. Constant is just 0. That would give me that derivative. Okay, you can always check for differentiating. Ooh, these are some good ones. So, you guys know some of these. I'm gonna flip ahead quick. You guys know the antiderivative of sine is negative cosine plus c. And you know the antiderivative of cosine is sine of u plus c. Now, you've been introduced to like the derivative of tangent, the derivative of secant, and you've been recognizing like their antiderivatives. So for example, like the antiderivative of secant squared is tangent. But what we haven't done yet is just straight up, what's the antiderivative of just tangent? Because that's not one that I know the derivative off the top of my head. I don't know what trig function, when I take the derivative of it, do I get tangent? Okay, same thing with secant, cosecant, and cotangent. We have those ones recognized like negative cosecant squared, that antiderivative. But we don't have like our basic 6 trig function, their antiderivatives. We don't know what they are yet. Here they are. Okay, I'm going to walk you through like a little proof for these two, and then these two are super similar, so I don't think we need to do all 4. But you can actually like do these using u substitution. You might. I feel like it's pretty rare on the AP exam to ask you one of these. They try to stick with, I feel like, sine and cosine and like secant squared and secant tangent, like the basic ones that you know in and out, derivative and antiderivatives. But it is possible that like this could show up on the AP exam, that you have to know these. I haven't come across a lot of problems, I feel like, when I've been looking at old exams where that it does come up, but your textbook says that it can show up on the AP exam, but I've never seen it before. So anyways, here's how you can easily find tangents. You can find them using trig identities. So that's the other thing, is like you don't know or have all the trig identities memorized. But tangent, this one you can recognize. We could rewrite tangent using like the quotient identity is technically what it's called. Rewriting this as sine over cosine. All right, so I'm going to let u be cosine. I'm going to let u be cosine. So that means that du dx is negative sine of x, which means du is negative x sine of x. And I'm like, okay, I see sine of x dx. That's good. So to get rid of that negative, I'd probably just divide it over and bring it out front here. And then we can go ahead and substitute that in for negative du. Now put the negative out there. Okay. So then it's an easy antiderivative. 1 over u, natural log of the absolute value of u, plus c. Back substitute back in, u was cosine of x. Okay, so there's a little proof of the antiderivative of tangent. So is this one on our list right here? That it's the negative natural log of the cosine of u plus c. I don't know why there's this extra bar here. I'm not sure. Okay. There's a little proof for tangent. This one's a little bit more intense, this next one. So I'm going to give myself some room here. Secant. So if this was secant squared, this would be really quick and easy. The antiderivative is just tangent, but it's not. It's just secant. Unfortunately. Okay. This is fun because we're literally like doing trig identities right now in pre-calc. So this is like, I get so much overlap here. Unfortunately, I'm the only one that recognizes that. All right, so what we're going to do to manipulate this, we're basically going to times this secant of x by secant of x plus tangent of x over that itself. So I'm not changing it at all. I'm really just timesing by 1. You would never know to like do this per se on your own, but this is kind of a trig identity that's going to help us simplify and allow us to use u substitution. Okay. There's a couple of trig identities you have, but they're pretty basic ones. Have to use in your homework. I put an example up here. Okay, so up top, that becomes secant squared plus secant tangent all over secant of x plus tangent of x. Okay, now I mentioned in a lot of these ones, like in your homework, you're often going to let u be like your denominator because we want to get it like in this 1 over u form because that's kind of the antiderivatives we're practicing. So looking at this, if I look at my denominator, secant of x plus tangent of x, and I think ahead to what's the derivative of secant? Secant tangent. What's the derivative of tangent? Secant squared. So I see its derivative located actually in the numerator. So I'm going to let u be secant of x plus tangent of x because I see its derivative is located in the numerator. Okay, so the derivative of what I called u secant is secant tangent. Derivative of tangent is secant squared of x. And then I'm like, oh, nice. I see that right in my integrand. Right here. Secant squared plus secant tangent dx. So I can substitute that all in for du. I don't even need to bring out any constants or anything. Okay, so the antiderivative is just the natural log of the absolute value of u plus c. Resubstitute back in u, which was secant of x plus tangent of x plus c. So that is where this one comes from. Okay. So I think if you ever get stuck on like a test and you can't remember this antiderivative for like tangent, would be easy to figure out like using u substitution. This is probably a little bit trickier, like recognizing, hey, I gotta multiply by secant of x plus tangent of x. These other ones, like I said, are super similar. Cotangent, just change it to cosine over sine. Cosecant, you do a very similar step right here to get the derivative. I'm gonna ask my calc friend at Mawanago how important it is to like memorize these for the AP exam, because I was under the understanding that it's not important, but your textbook said it is. So I need to check with some other professionals and see what the case is. I'm going to Mawanago actually after school today, so if I see her, I'll ask her. All right. So for now, what I'm going to say is don't worry about memorizing these because I don't think it's that important. So on your homework, if you see something like this where you have to know the antiderivative of cosecant, you can kind of use this as a cheat sheet. I almost kind of think of these as like trig identities, things you aren't expected to memorize. I would say what you are expected to memorize are like those basic ones like this. Oh yeah, antiderivative is tangent. I don't think those like blue ones are as common. But for now, since we have this cheat sheet with us, we can do some of these. So let's try a couple here. All right, so this 2x is located within my cosecant. So I'm going to let u be 2x because then I will have this. I will have the cosecant of u, and then I can use my cheat sheet because I know what the antiderivative of cosecant is. Okay, so I'm going to let u be 2x. And this works out pretty nicely because when I find the derivative, I just get 2. So there's no like double u substitution or anything wonky like that. I would just probably bring out that constant in front, that 1/2. And then we can substitute dx or 1/2 du. Like that. Okay. So like I said, for now, you can use your cheat sheet for this antiderivative. The 1/2 can just carry down. And I know the antiderivative of cosecant of u is negative natural log of cosecant of u plus cotangent of u plus c. Don't forget to resubstitute back in the 2x for u. So negative 1/2 natural log of cosecant of 2x. Oops. Plus cotangent of 2x plus c. With trig functions, guys, they usually leave them in the absolute value. They don't like put back that 1/2 power and write it as a square root. You'll more commonly see the trig ones left like in the absolute value. So I'd keep your answer like that. And that's a-okay. Okay. And I threw this one in here because this one might look like you use a trig identity, but you actually don't need it. And plus you see cosine and sines, and we should know those derivatives and antiderivatives really well. All right, looking at this one, do you guys have any inklings of what we might let u be?
Theta minus sine.
Okay, yeah, you're right. Why?
It's the derivative in the numerator.
Yeah, the derivative of theta is 1. Derivative of sine is negative cosine. I see the derivative in the numerator. Good. And again, like I said, a lot of these, try letting u be your denominator. If you're stuck in the 5.2 homework, put u as your denominator. All right, du d theta, this one's in terms of theta, would be 1 minus cosine of u, just like Mark said. So, pretty easy u substitution here. I have u in my denominator. Then I have 1 minus cosine d theta. That can all be replaced with du. So I just have a 1 in the numerator. Antiderivative, natural log of the absolute value of u plus c, back substitute in theta minus sine of theta. Okay, so just because you see a trig one doesn't always mean we might use one of those integrals, but be on the lookout for especially those new ones of tangent, cotangent, or tangent and all the reciprocal identities. All right, we're gonna do two with definite integrals, so ones with bounds. And remember, you guys know how to do this. The only difference now is I'm gonna throw in natural logs. And the other difference is your answer should be a number, right? Because now we're calculating the area under the curve. Here we're finding the antiderivative. Now we're calculating the area under this curve from 2 to 4. Okay, now this one's a little trickier because I just mentioned a lot of times we want u to be our denominator. In this case, we don't. Anybody know why we would not want u to be 3x? Or know why we'd want u to be something else?
Because the derivative is 1 over x.
Oh my gosh, Mark! Mark's on fire! Yes, natural log of x, 1 over x, the derivative is right in there. See that? We know the derivative of natural log of x is 1 over x, and I see that. I like that. I like the idea. Let's do it. So du is 1 over x dx. Okay, I'm going to substitute in what I have now. So I have the natural log of x is u. And then I see this 1 over x dx right here. What I don't have is this 3. No worries, it's a constant. Just go ahead and bring it out. So that'd be a third. So that takes care of that. So you don't really need this denominator, I guess. So basically we have u, and then x, 1 over x dx is du. All right, now for the bounds. So if you don't want to change your bounds, you don't have to, because I've noticed that some of you like to do that. I personally like to change my bounds and get everything in terms of u, because then I can just plug and chug from there. But if you want to anti-derive from here and then back substitute in and then plug in your bounds, you can do that. I'm just going to change my bounds. So they start off at 4 and 2, plugging them in here. So I get the natural log of 4 and the natural log of 2 as my new bounds. Okay, so that 1/3 carries down. Antiderivative of u, 1/2 u squared, add 1, divide by the new power. Plugging in natural log of 4, natural log of 2. Okay, so again, since I changed my bounds, I don't have to resubstitute back in ln x for u. So I would probably even bring that 1/2 out and treat this as 1/6 times each of those bounds squared. So we do upper bound minus lower bound. And honestly, I would be fine with you leaving your answer like that. This is a number. It's just not an exact number. The only thing I'd say, maybe recognize if you see it written like this. Because the natural log of 4 and the natural log of 2, those are not exact numbers. You might see it written like this. The natural log squared of 4. Instead of like the other squares. Or you might see the 1/6 distributed to it, but that's okay. That's a number answer. If the back of the textbook has a decimal, just crunch that number in your calculator. If you're expected to get a decimal answer, that'd be on the calculator portion of the AP exam for sure. Can't do that in your head. Okay, I like that one. Now this next one, we actually don't need to use u substitution. We're going to use a trig identity. This trig identity, you are expected to know the pi thing identities. Do you guys remember off the top of your head what 1 plus tangent squared is the same as?
Secant squared.
Secant squared. Height identity. These are fair game. I can give you a new identity sheet too if you want one. I have them printed out for you through class. So then that just becomes the square root of secant squared is just secant. And now I can use this cheat sheet. Now I know what the antiderivative of secant is. That was one we proved. It's right here. It's the natural log of the secant of u plus the tangent of u. Okay, so this antiderivative will be the natural log of the absolute value of the secant of x plus the tangent of x. And then we just plug in our bounds. Okay. Oops. That's not what I meant to do. So let's do this quickly. We got natural log of the secant. We plug in pi over 4 minus. Careful when you plug in 0 here. We actually don't get, just 0. We can't just kind of ignore it because I'm taking the secant and tangent of 0. So upper bound, I plug in pi over 4. Lower bound, when I subtract, I plug in 0. Oh boy, let's see how we're doing with our trig facts here. Okay. You guys know what the secant of pi over 4 is? Close. Wait. 2 root 2. Oh, 2 root 2. Yep, you're right. So that's just root 2. Yep, it's root 2. So if you don't know that, it's reciprocal cosine. Hopefully you know this sign. Cosine of pi over 4 is root 2 over 2. So I think what Mark was doing in his head was the reciprocal and then rationalizing it, which is beautiful. But that just simplifies to root 2. Okay, so that's root 2. Tangent to pi over 4? 1. Secant of 0? Cosine's reciprocal. Cosine is 1. 1. Plus tangent of 0 is 0. Okay. So we would get the natural log of root 2 plus 1 minus the natural log of 1, which is just 0. So it's actually just ends up being this. And we can drop these absolute values and replace them with parentheses if we want, because this number is going to be positive. The square root of 2 plus 1. That would probably be how you see the answer expressed. You don't have to actually add those together. Oh, perfect. We only have one more to go. We got 3 minutes to do this. Okay, the only other one I threw in here was, what if you're asked to find the average value? We know how to do this. The average value over any interval is we do 1 over b minus a times the area under the curve from a to b, f of x dx. Okay, so my interval is 1 to e. So I would do 1 over e minus 1 times the integral from 1 to e of 2 ln x over x. Okay, we've kind of done a couple like this now. Hopefully you're recognizing this again. I see that 1 over x, so I'm going to let u be the natural log of x. because I see like that 2 over x. It's very similar to the one we just did in number 1. So the derivative is 1 over x. Okay. And I will change my bounds as well. So u is the natural log of x. And then I see that 1 over x dx. And then I have that 2. So I'm going to bring the 2 out here. So it becomes 2 over e minus 1. And then I can substitute in directly for du. And I'm going to change my bounds. So e and 1. Natural log of e is 1. Natural log of 1 is 0. Okay. Anti-derive. 1/2 u squared. Plugging in 1, plugging in 0. Here's another thing we can do to make this easier. 2 and 1/2. So you'll just have 1 over e minus 1 times 1 squared minus 0 squared gives us 1 over e minus 1. I think that's the right answer. Yes, it is. We did it. Okay. Not to rush through, but just applying new integrals with something we already know how to do. How exciting. Okay, I still have one more lesson planned before our next quiz, so next Monday we'll start a new lesson. And we probably will have a quiz next week sometime. I just don't know which day.